Yeah, okay, so let's look at this problem. Right, so A is a fixed connection, so this is a cantilever beam, a series of point loads, and an applied moment at the end. In this problem, I want to find the internal forces at C. So I'm going to cut this right here at C. Now, do you want to work the left side or the right side? Yeah, what's the advantage of the right side? Well, I don't need to find any reactions. Okay? So I think I'll do that. Save myself some time. If you decided to use the left side, you would have to find these support reactions first. Okay? Everybody good with that? So the second thing we have to consider is, am I making this cut just to the left of C or just to the right of C? I don't know. We're going to have to check both ways. So I'm going to again look at this right side, but I'm going to make the cut just to the left of C, which means the 500-pound force is on my free body, CDE. Okay? So let me write this. I'll say we'll make the cut just to the left of C. So my free body diagram looks something like this. So I will include this half a kip force, and then I'll have this one here at midspan, then one here at the end, and then in addition I've got this moment of 2 kip feet. And this is a distance 10 and 10. Now, on that left face, I'm going to draw positive axial force, positive shear force.
So the significance of cutting it just to the left of C, so you can get all of those.
When I cut just to the left of C, I get this additional half kip force. Usually when you think about looking at the variation of shear force and bending moment along the beam, you start at the left side and you move to the right, kind of conventional X dimension. So I'm coming up to that force. I'm going to stop just before it, and then I'm going to do it again just after it, and we're going to see what changes as I pass by a force. I'm going to finish this by assuming a positive sign convention for my moment. So now what do I do? Solve the problem. So now I'm doing my statics, so I'm going to use right-hand rule for my moments, and I'm going to sum moments at the cut, like we talked about before, and make sure it's in equilibrium. So, what kind of moment with right-hand rule is this? Positive or negative? Negative. What about all these 1/2 forces? Negative. I'm going to pile them all together. They all have the same value of a half kip. The first one has what moment arm? None. So the second one has 10, and the third one has 20. And then out here on the end, what kind of moment is this? Positive or negative with my sign convention? Negative. So that looks like that the moment is minus 17. Is that right? Somebody check that for me. Does that make sense that the bending moment here is negative? Negative bending moment means that the structure kind of looks like what? Like Mr. Wilson, unhappy.
So
would this structure bend into a Mr. Wilson shape? Everyone agree? Except for Mr. Wilson. But the majority of us are correct. So that makes sense, right?
What was the A or the
axial force?
Yeah. Why did you choose those?
That's tension. right?
So you always assume tension.
I always assume positive sign convention when I make my cut. So that would be tension. And this shear force, that's positive shear force on that edge. And this is positive bending moment. Even though the value came out negative, that just means I have a negative bending moment.
And bending moment is always clockwise.
No.
Or positive bending moment.
A positive bending moment bends into kind of that smile shape we talked about, that convex shape. Right? Here, maybe this will help. How do you think this structure is going to bend, deflect with that kind of load? It's probably going to have some shape like that, right? What does that look like? It's a half of a sad face, so it should be negative bending moment. We got negative bending moment.
Well, when you did statics, you always assumed counterclockwise for moment. It's positive.
Statics.
I knew that. I must have missed when you did.
Right here, this is my static sign convention right-hand rule.
Okay.
But that's just for moment. That's just for accounting for the moments in statics. The resulting moment, now that we're calling it a bending moment, has a sign convention.
And those will come into play when we're doing
Well, when you communicate to another engineer and you say that beam has the largest moment, that beam is a negative moment, that means something. It's not arbitrary.
And then that's when your moment diagrams.
If you're designing reinforced concrete, you want to know where that is, right? Because reinforced concrete behaves differently than steel. Right? What if you had a negative bending moment in reinforced concrete like this? Where would you put the steel? Top. Because that's where the tension is. So if you just tell some guy, oh, I got a reinforced beam, it's got, I don't know, a moment in it. Well, you got to know if it's positive or negative. That's a big difference. Steel, not so much.
Hey, Dr. Kent, in mechanical engineering, where I come from, they always talked about positive bending moment being tension in the bottom. Is that not used in structural engineering?
Okay, you said tension in the bottom. What kind of bending moment?
Okay, a positive bending moment would be tension in the bottom and compression in the top.
That's correct.
Okay, but do you use that in structural engineering too?
It's the same. It's the same sign convention.
Okay.
I know it takes a little time to get used to. We've just been talking about this for a few minutes, so it's better to work it out now, right, than on the exam.
Yeah, it doesn't work too well.
Yeah, on the exam, you want it cold on the exam. You don't have to think about it on the exam. You just want to do it. Okay, so now I'm summing forces, and I'm assuming that up is positive. Okay? That has nothing to do with the fact that my positive shear force just happens to be up. There are two different things, not related. You could choose your positive sign convention to be down. It won't make any difference, as long as you're consistent. So with mine up, I would get a positive shear up, and I have half kip down, a second half kip force down, and a third half kip force down. And that's it. So what's my shear equal to? Looks like 1.5. And it's positive. Just to finish this off, I would then sum forces in the x direction. I'm assuming to the right is positive. And all I have is a negative axial force. That's it. Doesn't matter. It's zero anyway in this problem. Okay? So, the question becomes now, what if I move just to the right of C? So what changes in the problem? Well, my free body diagram is going to look almost the same, except I don't have this force here. It's now on the other side. I still have the half kip force in the middle. and on the end, I still have my applied bending moment of 2 kip feet. And I still have the same assumption for positive shear force, positive axial force, and positive bending moment. So, for equilibrium, I want to calculate the moment, so I sum moments at the cut. Using right-hand rule for my static sign convention, what do I get? Well, this moment is negative, and I have 2 forces creating negative moment. They have the same value, and they have a moment arm of 10 and 20. And then I have the applied moment at the end, which is minus 2 kip feet. So what's my moment? It's the same. So the moment didn't seem to change much as I went from one side of this force to the other side. What about the shear? Well, if I now sum forces in the y direction, assuming up is positive, I have my positive shear force. I have minus a kip, half a kip, minus another half a kip, and that's it. So my shear is 1 kip. What changed? On the left side it was 1.5. On the right side it's 1. What happened? I went past a half kip force. So it looks like the change in shear is going to be equal to the applied load. So if we're trying to write an expression or develop some kind of graph of the variation of shear along the beam, as I go from one side of a shear force or applied force to the other, the shear changes equal to the load. But it has no effect on the moment. So if I made a plot of the shear versus the length of the beam, and I'm looking for it happening or changing, let's say, just at this point C, what is the shear on the left side of C? 1.5. And then on the right side, it's 1. So the plot of shear has a step in it. And that step, the change in shear, is exactly equal to what? The force P. And why is it a negative change? Well, a force acting down with my sign convention is a negative force. You see that? Now, if I were to plot the moment, and granted, we don't know a lot about this yet, just to give you something to think about, we'll change. We know at point C, what's the value of the moment? It's still 17. Actually, it's negative 17. I probably should have drawn this on the negative side. Sorry about that. I'm going to put negative over there to make it work. Without telling you too much right now, the slope, the graph will come in at one slope and leave at another slope, but the value will be unchanged. So you can see that the curve will change based on the slope or the shear. And we'll make that more formal. I know we're just getting started, but I wanted you to start thinking about how shear force and bending moment are going to vary along the beam.
If we extended our plot for the entirety of the beam, it would just keep stepping up.
Which one?
Shear.
Yeah. And we haven't included the reaction shear. So we would start at some shear value and we would step down all the way across the beam. So the whole plot would be a series of steps.
The only thing that I'm hung up on is why is the bending moment clockwise positive, and then we have 2 clockwise bending moments and our value is negative.
don't think he understands the difference between an applied moment and a bending moment.
Okay, well, let me answer your question. Let me stop this first.